class. Today I'm going to introduce you to the second module of the course, and in this unit we're going to look at second order differential equations with constant coefficients. Now, you should be aware that there are multiple ways of writing the equations themselves. So here we have the traditional use of y prime and y double prime. In the second equation here, you can see that we use y dy by dx and d squared y by dx squared. And you should be familiar with both of those notations, but this one here is likely new for you. And here we use y and then capital dy and capital D squared y respectively. And the textbook uses all three of these notations, which is why I thought it was important to share that with you. Now, what we have are homogeneous equations because we have right side equal to 0 in these equations. So the question is, what possible y function could be used that would be a solution for this? Especially think about just the first form here. What could y be if the sum of these terms is 0? Well, a possible solution is one in which y prime, and y double prime are like terms. In other words, a solution where y prime and y double prime are simply multiples of each other. And you know a function like that, it would be the exponential function. So if y is e to the mx, then its first derivative would look like this, where we have m, the constant m, multiplied by e to the mx. And then y double prime would be the first derivative of this, so it would be m e to the mx times m again, or m squared e to the mx. So in fact, if we substitute this for y prime, and this for y double prime into this equation, it would look like this. If we common factor that exponential function here, we would get this. Now, in order for that to equal 0, it's this part here that must be 0. And that's because e to the mx can never equal 0. In order for e to the mx to approach 0, the value of m would have to approach negative infinity. Okay, so anyway, there is no finite way for this part to equal 0. So that means that am squared plus bm plus c is equal to 0. So from the original equation here, we find that this will be true only if this is true. And this is simply a quadratic equation. So like any quadratic equation, there will be three possibilities. We call this quadratic equation the auxiliary equation for the original differential equation. So it's the auxiliary equation. Look how closely it resembles it. And there are three possibilities. The roots will either be unequal and real, and this happens when the discriminant is positive, or there'll be just one repeated real root, which happens when the discriminant of the quadratic is equal to 0. Or finally, the roots will be complex roots, so no real number solutions, but complex roots, and that's of course when the discriminant is less than 0. So I'm going to do 3 separate lessons, one for case 1, one for case 2, and one here for case 3. So we are going to focus today on case 1, which is having 2 unequal real roots. Okay, so this is case 1, 2 unequal real roots. Okay, so that's the focus of our lesson today, and my intention is to go through 5 examples with you. So here is the first one. So to begin with, what we do is write the auxiliary equation that would correspond. Okay, so this that we're given is the original differential equation, and we're gonna go right here and write the auxiliary equation. AM squared plus BM plus C is 0. And so that will look like this. 2M squared minus 5M minus 3 is equal to 0. And now we're going to solve it to determine the 2 real roots. And you can solve it a couple different ways. This one is factorable, so I'll show you that, okay? So we want 2 numbers with a product of -6. That's 2 times -3. The sum of the numbers must be -5. So 2 numbers that would work here are -6 and a +1. So now we replace the middle term, and it would be -6m +1m. And of course, in either order here, we could have +1m and then -6m, and that would also work. Then we common factor the first 2 terms. 2m is common there, and that'll leave us with m minus 3. From these last 2 terms, it appears as though nothing is common, but we say that +1 is common. And that would also leave us with m minus 3 in brackets. These 2 terms match, and they have to. Okay, otherwise something is incorrect. So the common term here is m minus 3. And once that's removed, the second factor will be 2m plus 1. And so now the 2 factors are obtained by setting each of these equal to 0. So if m minus 3 is 0, we will obtain m is 3. Here, if 2m plus 1 is 0, then of course 2m is -1 and m is -1/2. So these can be m1 and m2 respectively. And so now all we have to do is write out the solution. And the solution will be y is c1 e to the m1x plus c2 e to the m2x. And so that looks like this. c1 e to the 3x plus c2 e to the -1/2 x. And here you can write -1/2 times x, or you could write -x/2, which would mean the same thing. And this is the general solution, of course, because it still has the constant c1 and c2 in it. And we have no additional information provided, so we are unable to solve for c1 or for c2. And so we are now done. Okay, let's try the second one. So again, we're given the differential equation. Okay, it's in this form. And we start by writing the auxiliary equation, which will look like this. And so for this example, this will be y double prime minus 4y prime plus y is 0. Sorry, that's just rewriting the original in a form that might be more familiar to you. and then from there you can write the auxiliary equation. But this was really optional. The auxiliary equation is this one, m squared minus 4m plus 1 is 0. 1 is the coefficient of y. Okay, so what I did was I took it from this form and wrote it in this form first, but that step is optional. And then I wrote this required auxiliary equation. And now we can see if it's factorable. If you like, we would need a product of 1 times 1, so a product of 1, while the sum would be -4. And that's not possible. So what this means is that the equation is not factorable. So what happens when it is not factorable? Well, now we use the quadratic formula, and I'll remind you of that. It's -b plus or minus the square root of the discriminant, and the discriminant is b squared minus 4ac. And in the bottom, we have 2a. Okay, so we have a is 1, b is -4, and c is 1. So we substitute into here. So the negative of b will be 4. So we have a 4 there. And then we can work out our discriminant in a moment. And the bottom would be 2 times a, or 2 times 1, which is 2. Okay, so now I need to do b squared minus 4ac. And you can try that. I'm just going to grab my calculator to show you that calculation really quickly. But you can try it. I think that you will get 12. Okay, so we're doing b squared minus 4ac. And it's these numbers here. So b squared. Now don't forget, when you square a negative number, you need to put it in a bracket if you want it to work out properly. So b squared, right? Minus 4 times a is 1 times c is 1. Okay? And then you can see it's just 16 minus 4. So you get 12. So that goes there. Now, normally, we would go to a decimal result here, right? We'd do 4 plus root 12 and then divided by 2. But we're not going to do that here. So what we want to do is reduce the radical. So what I mean is the square root of 12 is the same as the square root of 4 times the square root of 3. I'll show you that explicitly, okay? So you take 12 and you can break it into 4 times 3. And the reason we picked 4 here is because 4 is a perfect square. So you always take the largest factor of this number that is a perfect square. So I guess the smallest one of interest would be 4. 9 would be another one, 16, 25, and so on. So you're looking for a factor of 12 that is a perfect square like this. And the reason we do that now is because the square root of 4 is 2. So this becomes 2 times the square root of 3. So all we're saying is that the square root of 12 is the same as 2 times the square root of 3. Okay? And then further, we go one more step and we will divide each of these portions by 2. So 4 divided by 2 is 2. And then 2 root 3 divided by 2 is simply square root 3, like that. So this is our m value. So m1 will be 2 plus root 3, and m2 will be 2 minus root 3. And so then we now have our two real unequal roots. So we can write this now. C1 and C2 will remain, and we'll just be putting in our roots there. So that will look like this. C1 e to the m1 x plus C2 e m2 x, like that. Okay, so then that's pretty good. But we could also write this by recognizing here, this is the same as e to the 2x multiplied by e to the root 3x. And same thing here, this is the same as e to the 2x multiplied by e to the negative root 3x. So we could common factor, and we should common factor e to the 2x from those terms. And that will be C1 e to the root 3x plus C2 e to the negative root 3x left in the bracket like that. Okay? Okay, so that was our second example. Let's continue. I thought we would do, for our third one, a question where we'll be able to solve for C1 and C2. So not only will we get the general equation, but we'll also be able to find the particular solution as well. So we begin with this. Now, the first thing to do is make sure all terms are on the left side with right side 0 and in the right order. So here, this term will be next, positive 3y prime. So that is the correct homogeneous equation. Now we write the correct auxiliary equation. M squared plus 3m plus 2 is 0. Okay, and now, is this factorable? We would want a product of 2 and a sum of 3. This works with 2 and 1. Now, this is a quadratic equation with a leading coefficient of 1, unlike the first example we did, see, where the leading coefficient was not 1, so we had many steps in the factoring. But here, since the coefficient is 1, we can go right away knowing that the factors will be of this form. And these numbers being 2 and 1 gives us m plus 2 and m plus 1, just like that. And from here, we get our two values, right? We said m plus 2 is 0 and m plus 1 is 0. And this means m1 is negative 2 and m2 is negative 1. And so we can write our general solution. Y equals C1 e to the negative 2x plus C2e to the negative 1x, just like that. Okay, awesome. Now from there, we can solve for C1 and C2 if we use this information. So let's read what it says. It says y is 0 and y prime is 1 when x is 0. Okay, so I can first, since this equation involves x and y, I can first use this information. When x is 0, y is 0. So let's start with that. So when x is 0, y is 0. So what does that do? That means I can substitute 0 on the left and 0 here and here. That'll make each of these exponents 0. So we will have c1 e to the 0 plus c2 e to the 0, and therefore c1 times 1 plus c2 times 1. Or this equation, 0 is c1 plus c2. Okay, so that is not enough for us to determine yet these values, but I'm going to number it. That is one equation in two unknowns. And now we can also use this information. When x is 0, y prime is 1. But we don't yet have an equation for y prime. So we go back to our equation for y now, and we write an equation for y prime. So that means we are taking the derivative of the right side. Now, when you take the derivative of the exponential functions, the functions just repeat, but you multiply by the derivative of the exponents. The derivative of this exponent is -2. The derivative of this exponent is -1. So we end up with -2c1 e to the -2x plus -1, or in other words, minus e to the minus c2 e to the -x. Okay, so it's again -2 times c1 e to the -2x, and then it's plus -1 times c2 e to the -1x. Okay, and I've just written like this without the unnecessary addition sign here. It's just written like this. And now we can use the fact that when x is 0, y prime is known to be 1. Okay, so that's from here, y prime is 1 when x is 0. So both of these things are true when x is 0. Okay, so we can substitute now into here. So 1 is going to be on the left side. And then we're putting a 0 here and a 0 here. So what will we get? We'll get -2c1 e to the 0 minus c2 e to the 0. Or 1 is -2c1 minus c2. And that's equation 2. Okay, so I have one equation in two unknowns and a second equation in two unknowns. And so that is now enough to solve for C1 and C2. So I'm going to write those equations so that they are near each other. And now you can solve them using some methods we reviewed quite a long time ago. Including, you could use substitution. So what you could do is take the first equation and from the first equation write C1 is -C2. And then you could substitute that here. Where this C1 is, you could substitute -C2. That would be using substitution. Or you can use elimination. Elimination is when you make sure you have the same coefficient in front of one of the variables, but with opposite sign. For example, I have that here. In front of C2, here I have a positive C1, in front of C2, right here I have a +1 coefficient. And in front of C2 here, I have a -1 coefficient. So these are already set up for us to use elimination. So we would go ahead and add the equations at this point. And when we did that, of course, we'd get 0C2 So C2 is eliminated. And I would add here 0 plus 1. And I would add here 1C1 plus a negative 2C1 gives you a negative 1C1. Negative 1C1 or negative C1. And what does that mean? Multiplying both sides of the equation by negative 1, you end up with C1 is equal to negative 1. And if C1 is equal to negative 1, right, that would go right here. That means, so you could substitute into this one. So that would look like this. 0 is negative 1 plus C2. That means that C2 is equal to 1. This would go to the other side and we'd get C2 is 1. And now we have it solved. Okay, so elimination, the method of elimination. Also, it's sometimes called the addition-subtraction method. We could have done it instead here with by eliminating C1. If we were going to eliminate C1, what I would have done is I would have first doubled the first equation. So it would be 0 is 2C1 plus 2C2. And then I would be able to add, and C1 would have been eliminated first. Okay, so that would be certainly another option. All right, so now I know my values of both C1 and C2, so I just have to go back up to where we wrote the general solution and substitute those values, and I will now have the particular solution. So y equals, so where the C1 is, we put in negative 1 plus where the C2 is, we are substituting positive 1. And so that gives us our equation right here, okay, which we could leave like that. There are multiple forms, okay? Sometimes we would write it this way with the positive term first. You could also common factor this, so I'll show you another possibility. Then you would be dividing each of these terms by e to the negative x, and I guess this would be 1 minus e to the negative x here. Okay, so although I was happy with this first result, these are all possible answers as well. Okay, let's move on to another one, okay? So let's try this fourth problem now together. Sorry, just adjusting those blinds. It was getting a little bit sunny. So in problem 4, we have capital D squared y minus 4 capital dy plus y is 0. This can be compared with this form right here. And then we can move to writing out the auxiliary equation. Okay, and that would look here like this. M squared minus 4m. Oh, wait a minute. Have we done this question already? Huh. Which one? Yeah, we've already done this one. Sorry. Let me try again. Which one did I mean to do? Okay, oh yeah. This guy here? No. Oh yeah, this one. Okay, sorry, I'm just going to switch this real quick. We've done that question already. That'd be pretty rough to make you sit through the same problem twice. Just gonna switch this, sorry, I'm sure. Oh my Lord, I'm kind of making a hash job of this. Okay. Ta-da! Here's the question that I meant to do next. All right, the question is y double prime minus 4y is equal to 0. Okay, just finding the general solution. So the key here is that it's only 2 terms currently. One of the 3 terms are missing. Take a look. We've got the first term, and this is a y. So we have the last term. We are missing this term right here. So be careful when you're writing the auxiliary equation. You will only have this term and this term. So in fact, we're going to have 1m squared, and at the end, the number -4 equals 0. Okay, so just be careful. It's a little tricky. The middle term is missing. So this simply becomes m squared minus 4 is 0. And that's still considered a quadratic equation. Okay, and it can be solved a number of ways, but I'm hoping you realize that this is factorable right here. And in fact, this is what we consider to be difference of squares factoring. Since 4 is 2 squared, we now have this m plus 2 and m minus 2. Just like that. And so our values for m are obtained after setting these equal to 0, right? So if m plus 2 is 0, then m is -2. And if m minus 2 is 0, then m is 2. Okay, so we end up with these as our roots. We call it 2 real unequal roots. And so now that we have those, we go right to our solution of this form. And it'll be a general solution with C1 and C2 remaining. So it just will look like this. C1e to the -2x plus C2e to the +2x. Okay, and I should point out at this time that, you know, if I had written m minus 2 first and then m plus 2, then I would have m1 is 2, m2 is -2. And here then I would have C1e to the +2x plus C2e to the -2x. And there's absolutely no problem with that. That is also the correct solution. So you should know that you could have the 2 roots reversed here and still have the correct answer. And that's important when you go and do your homework and you're checking your solutions with those that the textbook provides, okay? So M1 and M2 can be reversed. All right, so even if we have C1 with a +2 and C2 with a -2 here, that would be correct. Okay, last one is this one here. Once again, we have only 2 terms. So one term is missing, but now look at the difference. This was a y, this is a y prime. This time it's the 3rd term that's missing. So we don't have this term here. So that's important. With the auxiliary equation, we will not have this term. We'll only have the first 2 terms this time. Okay, so that means that we are going to have the following: m squared plus 9m is 0. Okay, so while this one involved difference of squares factoring, it had these two terms. Okay, so this is a quadratic where the middle term is missing. Now we have a quadratic where the last term is missing. This kind of factoring is just common factoring. So m is removed as common, just like that. And then our two roots come from here. M is 0 and m plus 9 is 0. Okay, so m1 is 0. And m2 then is negative 9. And that means we can now write our general solution. And it is c1 e to the 0x plus c2 e to the negative 9x. Just like that. And of course, this is the same as 1, so we might as well simplify this. It'll just be c1 plus c2e to the negative 9x. So this is our general solution. And now look, I've got information here that'll allow me to find the particular solution. So I can start right away. I have an equation with x and y. So I could start right away by using x equals 0 and y equals 5. So we say at x is 0, y is 5. So that means 5 will be on the left side. And in the right side, I will have c1 plus c2 e to the 0, which is the same as c2 times 1. So 5 is c1 plus c2. And that is my first equation in two unknowns. Now, in order to generate my second equation, I'll need to use y prime. And therefore, I better figure out what y prime is. Here is y, okay? So we take the simplified version of the general solution and we differentiate it in order to find y prime. First, we differentiate the constant, and so that is going to give me 0. Okay, so we have 0 plus, now we take the derivative of this part, so it's going to be negative 9 times c2 e to the negative 9x. And so this is just y prime is negative 9 c2 e to the negative 9x. So this is our y prime expression. And now into it, I can use x is 0 when y prime is 18. So I'll do that on my next page here. So I'll just move this up a little bit so we can still see it. Okay, like that. So here's my y prime expression. And again, I'm going to use when x is 0, y prime is 18. Okay, so that means 18 will be on the left side. And we're putting a 0 here again in our exponent. And so this is the same as 18 is negative 9c2. And therefore C2 is negative 18 divided by, C2 is 18 divided by negative 9. So C2 is negative 2. And I've already got C2 determined in my second equation. Now I can use that value in the first equation. So we're gonna have 5 is C1 plus negative 2. Okay, plus negative 2, or in other words, 5 is C1 minus 2, and this means C1 is 5 plus 2, or C1 is 7. Okay, and now we're all set. We go back to the general solution here, and we can write the particular solution. So it is y equals C1, which is 7, plus C2, so plus negative 2 times, so we can just write minus 2, e to the negative 9x, just like that. Okay, so that was the general solution and that was the particular solution. Okay, so those are the 5 examples I wanted to go through with you today. You can see that as long as you're able to solve quadratic equations and solve 2x2 linear equations using perhaps the method of elimination, then this unit is pretty straightforward. In fact, we don't even need to know how to integrate for this unit of the course. So it's kind of a nice, refreshing change maybe as compared with the first unit, which was all very heavy integration. So please start to practice this. I've got the recommended problems from your textbook outlined for you in Blackboard. Okay, thanks so much for watching and have a great day.